Yo, what's up, Sci Fam? It's your boy Nickel, and today we're going to take a look at absolute age dating. Now, this is a two-parter because first we got to understand and review some concepts from some chemistry that you may have had in the past. And so we'll dig in here as you can see it organized on that science notebook outline. So we're looking at absolute age dating, and this here is a technique that we can use to determine the actual factual age of a rock layer. And we can do this using something known as radiometric dating. So we have an actual way to get at the age of the rock. Unlike relative age dating, absolute age dating is going to give us an actual age of a rock layer. So let's see what we need to understand so we can get a better idea of what radiometric dating is, so that we can have a grasp of how it's used to get the age of a rock layer. So to begin with, we have to start by defining an isotope. And an isotope is just a single type of an atom. And if you remember what an atom is, well, it's the structure of any element on the periodic table of elements. Each element on the periodic table, if it's by itself, it's considered an atom. And in the inside, there's the nucleus, and on the outside are the electrons that are zooming around the outside of the nucleus. So if we look at what an isotope means, it means that we have a single type of those atoms, and that atom can have a different number of neutrons in the nucleus. So there's protons and neutrons located in the nucleus, which I'm showing there in the blue and the purple, just representation. The outside zooming around are the electrons, and again, there's just a couple there. That's not to scale, size, or accurate in any way. It's just a depiction of something we'll use there to define isotopes. So an isotope is a single type of an atom, but a single type of atom can actually have different numbers of neutrons in its nucleus. And it doesn't change what the actual element or the atom is. So let's take a look at a famous one here known as carbon. So we'll draw a box around it to show that this is the element carbon. The C is the element of carbon. So here's 3 different atoms of carbon. Now we could have carbon 12. So there could be 12 neutrons in the nucleus of this carbon atom. But carbon also can have different isotopes. It can also have 13 neutrons in the nucleus, and carbon can also have 14 neutrons in the nucleus. So I'm just going to draw those representations there to show that an example of an isotope is carbon. It can have 3 different isotopes. It can have carbon 12, carbon 13, or carbon 14. And that's how we typically would say that. It's carbon 12, carbon 13, carbon 14, and so on, depending on what the element is. Now, remember that term we had before, radiometric dating? Well, radiometric dating is a process that relies on something known as radioactive decay, which is how it gets its name, radiometric. The radioactive decay is something that happens inside of one of these atoms. And in these atoms, or in these isotopes, we will say that some isotopes are actually unstable. Some of them, like carbon 12, carbon 13, carbon 14. Carbon 14 is unstable. It breaks down, and when it does break down, it loses some of those neutrons in the nucleus. It loses some of the stuff that makes that atom the atom, and when it does, it actually forms a new element, a whole new element. It's no longer carbon anymore when it goes through radioactive decay. So the difference between different elements in the periodic table of elements is that there's different protons in the nucleus. It has different nuclear structures, so therefore as the nucleus changes in the isotope when it breaks down, because it's unstable, it becomes a whole new element. All right, so radioactive decay then, if we're going to go ahead and define radioactive decay, it's a random process. And it's a random process of at one moment, some moment in time, one little tiny atom inside of a sample of rock, let's say, just breaks down and it goes through radioactive decay. It's a random process. We don't know when one of them is going to happen. But it's kind of like a coin. If you flip a coin, you might get 7 heads and 3 tails. That means that 70% of the time you're getting heads. However, if you flipped a coin 5,000 times and you had 5,003 heads and you had 4,997 tails, well, that's going to be about 50%. Even though you have 3 more heads than tails, still you have so many numbers here, it ends up being about 50%. When you have less numbers and less trials and you have only 3 out of 7, well, I'm sorry, when we have 7 heads out of 10 total flips of the coin, we end up with about 70% heads. So down here, it'd be more like 5,003 over the total number of times we flipped the coin, which is 10,000, and that would give us the 50%. So regardless of this situation, what I'm trying to explain here is that the more trials we have, the more close we get to the actual probability of an event actually happening. So radioactive decay is a random process, but over a large number of events, meaning that there's tons of atoms in one sample of rock, well, that decay rate in which it breaks down into a new element actually becomes predictable. So radioactive decay happens spontaneously. It's a random process, but it happens over a long period of time. So if we wait 1,000,000 years or thousands of years, it's been such a long amount of time in which we've given those atoms to actually break down from isotopes into other elements, that radioactive decay rate actually becomes predictable. And we'll dig in more into that in our next part to look at some actual examples of some radioactive decay rates. And instead of calling it a radioactive decay rate, we typically will use the term of a half-life. And half-life means it's an amount of time that's required for half of what we're going to call the parent isotope. So what we start with, like for example, carbon-14 would be the parent isotope. Carbon-14 breaks down into a different element, nitrogen-14. So the parent isotope would be carbon-14. Let's put this down here as our example. Let's say we have carbon-14. We draw it just like that. This is going to decay into a new element. It's now going to be nitrogen, and nitrogen is going to have 14 neutrons in its nucleus, so we call it nitrogen 14. So going back to half-life, the half-life is the amount of time required for half of the parent isotope to decay into what we were going to call the daughter atom, or the daughter isotope. So here, carbon-14 is our parent, and nitrogen is the daughter. So in order for this to happen, for carbon-14, for example, it takes something like over 5,000 years for us to go from a full sample of carbon-14 to half of the atoms in that sample of rock to turn into nitrogen-14. So let's imagine over here that we have a rock. This is a big piece of rock. It's all made out of carbon-14. After a little over 5,000 years, half of that carbon-14 in that rock sample is now nitrogen-14. And about 5,000 years later, half of that carbon-14 is then broken down, and that becomes nitrogen-14. And another about 5,000 years later, half of what's remaining of the carbon-14 turns into nitrogen-14. And this is going to keep happening. So half of that carbon-14 turns into nitrogen-14. And it keeps on going, half and half, every 5-ish, a little over 5,000 years. The actual amount of time it takes for carbon-14 to turn into nitrogen-14 is 5,730 years. So every time I split that in half, 5,730 years had gone by. All right. So using that example, we can take that little box drawing that we just did, and we can make a table here to look at how much parent atom there is and how much daughter atom there is over different periods of half-lives. So if there's no half-lives that have happened yet, meaning that we have the original sample, then we're going to have 100% of our parent atom. When one half-life occurs, well, it's going to break in half, and only half of the sample is going to be made out of our parent atom. When 2 half-lives have happened, then we're only going to have half of that 50% left over, so now we're going to end up with 25% of our sample is going to be made out of that parent atom. When we get down to a third half-life, well, we have to half the 25%, so that would be 12.5% is just still our parent atom. By the time we get to our fourth half-life, you can see we're getting to the very, very small percentages here. We'd have 6.25% of our original sample would be the parent atom. But you see, it's going to have to add up. All of the sample is still there. None of the sample is left. It's just converted from carbon, for example, into nitrogen. So when there are no half-lives that have happened and we have 100% of our sample is the parent atom, that means that none of our sample is the daughter atom. When we have 50% of parent atom, well, then that means that 50% of the sample will now be the daughter atom. When we have 25% of our sample is still the parent atom, that means that 75% has converted and become the daughter atom. We can continue on. In the third half-life, 12.5% would be the parent atom. We have 87.5% is now the daughter atom. And finally, in the fourth half-life, 6.25% of the sample is the parent atom, leaving 93.75% of the sample, which is converted to the daughter atom. And this can continue on beyond 4 half-lives. So let's do a quick graph here to kind of show what's happening over time. So to show 4 half-lives, we're going to have to put the half-lives here on the x-axis. So draw some equidistant marks down here, and we're going to write half-lives. And we'll number these. We have 0 on the x-axis where it crosses the y, then 1, 2, 3, and 4 half-lives. Now, up to the top of our y-axis, we're going to just go ahead and put 10%, because this would be 0%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. And so what we drew over here on the y-axis is the parent, the percent of parent isotope. Now, we just made this table so we can easily graph our data. So when we have 0 on the x-axis, when we have 0 half-lives, we have 100% of our parent atom is there. When we have 1 half-life, we have 50% of our parent isotope. After 2 half-lives, we have 25% of our parent isotope. After 3 half-lives, we have about 12.5, and I'm just estimating here, and 4%, we have about 6.25% of our parent isotopes. So if I get out my highlighter here, I can draw a line that kind of connects these. You can see, without that little bump at the end, that's definitely not going to bump up. You can see that it just consistently declines. The amount of parent isotope consistently declines. So what this means for us then as scientists is that after so many half-lives, radiometric dating, which is this topic that we were discussing here of how atoms break down into new elements, radiometric dating, it's just no longer useful. But when it is useful, it's super cool. So let's take a look at part 2, which will look at types of radiometric dating, how we can do it in different elements that decay into different types of atoms. I'll catch you over there on part 2 of absolute age dating.